Oh, there we go. There we are. All right, very good. So we're going to talk about the state of the art in telephone switching before computers came along. And when we think about telephones and telephone switching today, we know that computers today are heavily involved. They're running everything. But telephone switching goes back 130 years. It was not just, not 15 years after Alexander Graham Bell invented the telephone that automatic switching first started to be developed. And that, of course, is way before computers. So we're going to be looking at the various systems that existed back then and kind of how they evolved and the complexity of what was involved in telephone switching and the telephone network back in the day. I got interested in this back when I was an undergraduate at MIT. My big student activity was hanging around the MIT radio station, which happened to be located next door to the switch room for MIT's dormitory telephone service. And Dorm Phone at MIT was a privately owned phone system not connected to New England Telephone, because you couldn't do that back in the 60s, that had a phone in every dorm room. And it was a step-by-step switching system, which is one of the things that we'll talk about today. And I thought that was kind of cool. And I needed a part-time job, and I decided that working for Dorm Phone was going to be a lot more fun than working for dining service. So I got myself a part-time job as a Dorm Phone technician, basically. And then I got into MIT's co-op program, and I did my co-op assignments at Bell Labs in Holmdel, New Jersey. And my first summer there, I would basically quickly eat my lunch and then go scurry to the library and read everything I could about switching systems in the Bell Labs library. So that was kind of fun. And then in the 70s, when MIT started doing independent activities period in January, and you could do special classes, short seminars on different subjects and whatnot, I spent a week teaching a class on telephone switching. So that's my background in doing this, and something that I've always been interested in. And preparing this talk gave me a chance to relearn a whole bunch of things that I've forgotten over the years. So we'll see how this goes. So what we'll cover today is some of the early development of telephone switching, some of the general concepts, and then I'll spend most of the time talking about the major non-computerized telephone switching systems that have existed, particularly in the Bell system over the years of its existence. And so we've got 4 of those to cover. So let's go back to the 1880s. The telephone was invented in 1876 by Alexander Graham Bell. And his vision for how it might be used originally was, you'd buy a pair of them and you'd have a telephone that in your house that would connect you to the barn, for example. And it was quickly figured out that really the value of this new invention was in enabling anybody to be able to talk to anybody else who had a telephone. So we needed some form of switching and the ability to interconnect different people's telephones. And once that idea was hit upon, it was pretty quick that the telephone started to be adopted throughout the country. So you'd have a town and people would have their telephone sets in their homes or in their businesses. And each phone would have a pair of wires that converged on a switchboard in some central location in town. And this, of course, is a manual switchboard where calls were completed. And there were telephone operators who had their office there. So this is the concept of the central office for telephones. And interestingly, I read that the first telephone operators were actually teenage boys. And teenage boys were hired to do this job because they performed very well as telegraph operators. But it was quickly found that teenage boys were not the best folks to actually be talking to people who wanted to make calls. They didn't necessarily have the right attitude. They didn't have the right amount of patience. And so very quickly, the telephone operator job became a job for women. And so we usually think of telephone operators as women. And a little bit later, I'll have an interesting statistic about that. Now, in this day, there was no such thing as long distance, of course. You couldn't have a telephone call go any farther than the signal generated by a telephone could successfully propagate down a pair of wires. So most calls were within a town or to an adjacent town, within some fairly small area. if you really wanted to get in touch with somebody across the country quickly, you'd still send a telegram for long distance messaging. So we're mostly concerned about telephone calls within a fairly limited area.
Can
And so,
each telephone was a dedicated pair of wires that went from your house to the switchboard at that point?
Yes, that's correct. And
it's an important distinction.
Yes, and you know, I mean, in terms of conventional, you know, old-fashioned, plain old telephone service today, that's still true. You've got a pair of wires. It's in a cable with a bunch of other wires, other pairs of wires. But yeah, that you've got your pair of wires that goes back to the central office, certainly.
But the difference was the first ones were dedicated. The red and the green wire in your house ended up being the red and the green wire that was in the switch, versus today, God knows where they are.
Well, once you get, but if you have, you know, if you still have copper wire telephone service from Verizon, you've got a pair of wires coming to your house, and you can trace that pair of wires all the way back through a number of cables as an individual pair of wires all the way to the central office. That's still true.
Oh, really? I thought everything was multiplexed now, so that
they can be multiplexed over some part of that, but I mean, it starts out as a pair of wires at your house and it ends up as a pair of wires back in the central office. So there may be some multiplexing in the middle. Yeah, that's true. There is that as well. Okay, so here's a photograph of an early telephone switchboard. I was talking about the 1880s, but this photo is actually credited to 1904 in Richardson, Texas. But we can't tell, you know, exactly when this particular switchboard was built. And directly in front of the telephone operator, of course, is the field of jacks that represent the subscriber lines that might want to make a phone call. I suspect that the little strip of jacks to her left, where you see the white cord reaching across, those are probably jacks that represent trunks to other towns. For completing calls to other central offices. That's my guess as to what that is. And so you see the cord sets that the telephone operator uses. You know, plug one end of a cord set into the originating line's jack, and then there's a second cord that she'll pull up and plug into the jack of the line of the called number. And you know, we still see plugs and jacks like this today. You know, we're all familiar with this kind of plug. We have miniature versions today that we use for our headphones and so on. But really, these were developed for telephone switchboards in the first place. And ignore the text that's in parentheses here. I really just want to talk about the configuration of the plug. I mentioned that, you know, the telephone line has two conductors. One of them is connected to the tip of the plug. The other one is connected to the ring of the plug. And then there's a third conductor in the plug, which is the sleeve, which turns out to be fairly important in telephone switching, not only in manual switchboards, but in automatic switching as well. Basically, the idea is that within a telephone central office, the sleeve lead indicates, the sleeve lead is associated with a telephone line in the central office, and it indicates whether or not that telephone line is in use. So telephones are powered by battery from the central office. It's 48 volts DC. And so whether something has battery potential on it or is grounded is a distinction that's made throughout telephone switching. So with a manual switchboard, basically, if a telephone number is otherwise engaged, the sleeve lead associated with it will be grounded. And if somebody wants to call that number, the switchboard operator reaches and she's about to plug in the plug into that number's jack, the tip of the plug will touch the sleeve of the jack. And if that sleeve is grounded because the line's already in use, the operator will hear a click, and she'll know that's a busy line and she shouldn't plug in because that would barge in on an existing call. Now, the interesting thing is that we don't much use plugs and cord sets for completing telephone calls, but the nomenclature that started around this has stuck. And throughout the telephone literature, the two wires that comprise telephone, the two wires of a pair that comprise a telephone line are still referred to as tip and ring. The two wires are referred to as tip and ring. And within a central office, the lead that indicates whether or not a line is in use or not is still called the sleeve lead. And this follows all the way throughout the literature. Okay, so we'll keep that in mind as we go along here. I'd now like to introduce you to Mr. Allman B Strojer, who's a very important figure in our story today. He's born outside Rochester, New York, served in the Union Army. He started as a school teacher and then, for whatever reason, changed careers and became an undertaker. And by the 1880s, he was in Kansas. Different biographical things I've read have put him in Topeka or maybe Wichita. We know that by the early 1890s, he was living in Kansas City. But somewhere in a town in Kansas in the 1880s, he was an undertaker. And he was a man who had a business problem. The business problem was that he was one of two undertakers in town. And he discovered that he was losing business. And he was trying to understand why. And, of course, in these days, people, if they needed the services of an undertaker, they would call up the telephone operator, and maybe they didn't even know the telephone number of the undertaker. They just asked the operator, "Connect me to the undertaker, please." Turned out that one of the telephone operators in town happened to be the other undertaker's wife. So Mr. Strojer suspected that if somebody called up and said, "Give me the undertaker," the operator would connect her to her husband rather than to Mr. Strojer. So he was thinking, wouldn't it be nice if you could make a telephone call without involving a human operator? Well, turns out that Mr. Strojer was kind of a tinkerer and a bit of an inventor. According to biography that I looked at when he was a kid, if his parents asked him to do a chore, he would just as soon spend his time trying to figure out some contraption to make that chore easier than he would actually going off to do the chore. So it was sort of natural that he would tinker and maybe try to come up with some idea for an automatic telephone switch, which he did. He actually patented a device in 1891 that was successful. And something similar to the middle photograph that you see here. And I suspect that this drawing on the right is probably a patent drawing or something like that. But it's reported that in his first model, when he was just trying to conceptualize this, he used a round shirt collar box and a bunch of hat pins for contacts for his switch. Well, the device was actually successful. He formed the Stroger Automatic Telephone Exchange Company, which later became Automatic Electric, which ultimately became the manufacturing arm of General Telephone, or GTE as we knew it later. Automatic Electric was the manufacturing arm of GTE, just as Western Electric was the manufacturing arm of AT&T. So the first installation of the Stroger system was in a town in Indiana in 1892, and it had 99 lines that it could handle and reportedly had 75 subscribers. The telephone dial had not been developed yet. So in fact, associated with each telephone, there was a kind of a telegraph key that the user could tap on to give the number of taps corresponding to the number that you wanted to connect to. And so that's the original Stroger switch mechanism. Now, Stroger switches and the step-by-step system that they were used in were actually the most common type of electromechanical switching system, really as long as there were electromechanical telephone switching systems. There were bigger ones, there were better ones, but step-by-step using Stroger switches existed throughout the history of switching well into the 1980s. So here's, this is actually a photo, the card that I kind of cropped at the top suggests this is taken in a museum of some sort. The card is in French, so maybe this is in Quebec or maybe in France, I don't know. But this is typically what a Stroger switch would look like with a cover removed off the top part. The top half of the switch had several relays that basically provided the logic for how the switch operated. You can see there's a mechanism, a ratchet and pawl mechanism that could raise this rod up and down. And then there's a similar mechanism that's a little bit hard to make out in this picture that could rotate the rod as well. So a Stroger switch basically has 2 degrees of motion. It's got a rod that moves up and down, and you can see the wipers on the contact banks down at the bottom. They will move up to a particular level, and then the second motion is that the wiper arm would rotate to access one set of contacts out of the 100 sets of contacts that are on the bank. Here's a drawing that maybe makes it a little clearer. You can see more clearly the wiper arm and the contacts and so forth. So basically, a Stroger switch provides a 1 out of 100 selection. That's been true for the history of Stroger switches. Oh, in the photo that we looked at before, you can see there are actually 2 contact banks. And that's because a given contact bank can have 2 contacts, one above and one below, as you see in the diagram on the right. And we need to carry 3 leads associated with the circuit: tip, ring, and of course sleeve. So the second contact bank down at the bottom just is carrying the sleeve lead with it. So we step back from Stroger switches and talk about an important concept in telephone switching, which is the 3 stages in a switching network. I mentioned that the Stroger switch could access 1 out of 100 contacts. So if you want to have a telephone exchange that was capable of calling 100 lines, you just need 1 Stroger switch. You could have a Stroger switch for every originating telephone, and somebody could dial 2 digits, and the switch would first step up for the tens digit, and then the second digit would rotate and reach the contact of the individual line. And that's how you could do a telephone exchange with 100 lines. Well, that's not terribly economical. If you have 100 telephones, not all of them are going to be in use at the same time. So it's really not economical to have 100 Stroger switches, 1 for each telephone. And of course, as you expand beyond 100 lines, the switching pattern becomes a little bit more complicated than that. So we evolved to this 3-stage switching network, which actually is true in all of the kinds of switching systems that we'll be looking at today. The first stage is concentration, then distribution, and then expansion. So the idea is that we want to be economical about how we use our switching equipment. So we want to be able to provide access to the switching network for all the subscriber telephones on the left side there, but not all of them are going to be in use at the same time. So we actually have a concentration function. Then we route our calls through the switching network, that's distribution. Then when we get to the point where we're ready to connect to the called subscriber's line, we have the expansion function, which is analogous to what I just described with the Stroger switch accessing 1 out of 100 lines. So this principle is going to carry through to every switching system that we can think of. So here is a diagram of step-by-step switch train for 4-digit dialing. So we've got a 10,000 line exchange. We just have to dial 4 digits and we'll be connected to the called party. So this runs left to right. We start with the calling telephone on the left. The caller takes the telephone off hook. That closes a DC current path through the telephone, and that's detected by a line relay. There's 1 line relay for every telephone line in the exchange. The line relay says, "Hey, this line wants service," and it causes a line finder to start to connect to the calling telephone's line. Now, line finder is a Stroger switch, so it selects 1 out of 100. And what a line finder does is, under the control of some bits that aren't shown here, but the line relay says, "Hey, this number wants service." Let's say it's 68. The line finder serves a group of 100 lines. The phone goes off hook, the line relay closes, the line finder circuit operates, and the line finder now steps up to the level and then rotates across and gloms onto the calling telephone's contacts on that line finder contact bank. And now that line finder is directly connected to a first selector, and that first selector provides dial tone to the caller. Now, a selector, again, these are all Stroger switches. So the first selector basically takes 1 digit. the caller dials his first digit, the selector steps up to the appropriate level, and now it rotates automatically and hunts for an idle second selector to take the caller's second digit. And so we go on to the second selector, the caller dials their second digit, and now we've gotten down to the hundreds. And so now we go to the connector for that hundreds group, and that works just as I described a little bit ago. That actually accepts 2 digits from the caller. The first digit steps up to the tens group, and the second digit rotates to find the actual called line. And that's basically how the step-by-step switch train works. The connector then rings the called telephone, provides ringing tone back to the calling telephone. When the called party answers, it cuts through a talking connector. Basically that's the telephone circuit, and that's how step-by-step works. I'm going to show a video that will demonstrate this, but first I will stop and ask if anybody has any quick questions before we do the video.
Yeah, Ken, this all looks to be a one-to-one system, but my recollection when I was a kid is that many of the phones were party lines.
Yes. Right. There's party line stuff going on here. I'm not going to get into that because there isn't time. But basically, party lines. Well, I'll mention one thing, which is if you have a 2-party line, each party gets ringing current differently. The bell on a phone on one party is connected to between one wire and ground. And the other party is connected between the other wire and ground, and the connector knows which line to send the ringing current, which wire to send the ringing current down. It's referred to as tip ring or ring ring.
I used to call my the woman who became my wife. I used to call my girlfriend. She was on an 8-party line, and the ring had a peculiar sound, so everybody knew it was a long distance call coming in. And so we'd get 8 parties answering the phone, 7 to listen to what we were saying. And that would load the system to the point where we had to give up, and she had to drive 5 miles to town so we could talk on a
Technically, you could do a 4-party line without having everybody's phone ring. The 4 parties could ring independently with some technical trickery. Anything more than that, out in the boondocks, there used to be different patterns of ringing, and you have to listen for your pattern of ringing to figure out whether the call is for you or not. But that's another whole aspect that we're not going to get into. What I'd like to do now is show a video. It's interesting. The Bell system, of course, did not invent step-by-step, did not invent Stroger switches. They actually licensed Stroger's automatic electrics patents, but they did manufacture a lot of step-by-step, and a lot of especially rural and outer suburban offices in the Bell system were step-by-step. So this is a Bell system video about the step-by-step system, and it really makes it sound like it's the best thing since sliced bread. But that's what we'll do right now.
Hundreds of telephone buildings like this one throughout the Bell system house the automatic dial equipment that makes it possible for customers to dial their calls accurately and quickly. So quickly, in fact, that the bell rings almost as soon as the last digit is dialed. This accuracy and reliability did not just happen. No, indeed. It came of careful engineering, manufacturing to close tolerances, proper installation, and last, but by no means least, proper adjustment and care by telephone men who know their circuits and equipment thoroughly. Here we see a part of the dial equipment to take care of 20,000 customers. It represents an investment of about $2 million. In this particular city, the switching equipment is called step-by-step. It got its name because each call progresses through the office a step at a time as each digit is dialed. To telephone people, a knowledge of how this equipment works is basic to proper maintenance. Demonstration setup that we will use to show how a call progresses through a 5-digit step-by-step office. It is composed of 5 devices called switches. When the calling customer raises the receiver, a circuit is closed, starting the first switch, which is called the line finder. We'll do it again in a moment. Watch the line finder hunt the calling line. Also, watch the contacts of the line finder shaft, which we call wipers, step in to connect with the calling number's terminal. Now see it happen. The line finder is connected permanently to a first selector, which returns dial tone to the calling customer to tell him that the equipment is ready to receive the first digit. For this demonstration, we will dial the number 35286. The circuit is connected to contacts controlled by the telephone dial. As the dial is moved off normal for the digit 3, no action takes place in the first selector. But as the dial returns to normal, the selector will respond to the dial pulses. It stepped up to the 3rd level, and by rotary action, cut in automatically to select an idle circuit to the next selector. This is the 2nd selector. This switch will operate when the 2nd digit is dialed. The next digit is 5. Again, nothing happens as the dial is rotated to the finger stop. But watch the 2nd selector as the dial returns to normal. It stepped up to the 5th level as it responded to the 2nd train of dial pulses and cut in automatically. The 2nd selector extends the circuit to the 3rd selector. This selector operates in the same manner when the next digit, digit 2, is dialed. The selector stepped up to the 2nd level as the dial returned and cut in. The 3rd selector extends the circuit to the connector switch. The connector operates somewhat differently from the selectors, as we shall see when we dial the first of the last 2 digits. The next digit to be dialed is 8. As the dial is moved to the finger stop, no action takes place in the connector. But when the finger is removed, the connector will respond to the dial pulses and step up to the 8th level. Notice, however, that it did not cut in. This is because it is now necessary to select the called party's terminal in the connector bank. The equipment waits for the final digit to be dialed. The 5th and last digit in this demonstration is 6. As the dial returns to normal, the connector rotates to the 6th terminal. The connector now sends ringing current out on the called line until the receiver is raised. Now let's watch another call as it progresses step by step through the demonstration equipment. If the number this subscriber is calling is in use, the connector will recognize the busy condition and will return busy tone to the calling customer. Let's see how one of the switches used in establishing this connection actually operates. The principles of operation of the first selector are basic to other step-by-step switches. It looks rather complex, so let's put it in a special stand where we can take a good look at it. Actually, it consists of 5 relays designated A, B, C, D, and E. Magnets and mechanical linkage step the shaft vertically. Magnets and linkage also rotate the shaft horizontally. A release magnet and armature release the shaft when the call is completed. This constitutes the mechanical part of the selector. The electrical part of the switch operation is shown in the circuit schematic. This tells a simple story to the experienced telephone man. In some cases, it is difficult to realize the effect of various adjustments on switch operation because of the speed with which it operates. The complete operation takes less than 1 second. However, with the Fastax camera, action can be slowed down as much as 200.
Okay, I'm going to pause here, and because we've got a lot of other stuff to cover, but I think you get the idea of how the step-by-step switch works. So let's go back to the presentation. There we are. Okay. Got the presentation back on the screen? We're good? All right, thanks. Okay, so that's step-by-step. And there's a lot of step-by-step installed as the most commonly installed electromechanical switching system over the decades, but it's got some limitations, and I've kind of listed those here. It's well suited to small to medium-sized installations, 4-digit dialing, 5-digit dialing within a town or a small city. It's a little bit harder to handle larger numbering plans than that. As we went in this country to uniform 7-digit dialing, special techniques were developed for step-by-step, including digit absorbing selectors, where you would dial a digit and the selector would say, oh, that's nice, but that's just the first digit of my exchange code, and it would drop down again and wait for the next digit to be dialed, stuff like that. The system is not terribly well suited to large urban areas in the Bell System's estimation. Nonetheless, a lot of other independent telephone companies stuck with step-by-step in large metro areas. Probably the biggest metropolitan area that stuck with step-by-step until electronic switching came around was the Los Angeles area, where General Telephone was the incumbent telephone provider, and the entire LA area, except for downtown LA, was step-by-step. So the Bell System had the telephone franchises in the largest metropolitan areas, New York, Chicago, Boston, major cities across the country. And although they did license the Stroger patents and build step-by-step, they felt that it wasn't well suited to these large urban areas. And so the Bell System focused on developing something else that would be better for large urban areas than step-by-step. So they stuck with manual switchboards through the early 20th century. And in fact, in New York City in 1920, New York Telephone employed 19% of the women who they felt were eligible to work as telephone operators. And they estimated with the growth of telephones by 1930, if they didn't have automatic switching, they need to be employing 43% of the women who qualified as telephone operators, which is quite amazing and a good motivation for developing something better than step-by-step. Well, the Bell System's better than step-by-step was the panel switching system. And that's shown here in a very old photo. And panel was named after these basically panels of switch contacts that are on these frames, these vertical frames here. And you can see in front of these dark panels, there's little white spots, and those are actually connections in progress in the switch. And we'll see how that works. So the panel switching system was specifically designed for large urban areas. It was developed in the second decade of the 20th century and saw its first deployment in the New York area, basically during World War I. And it became extensively deployed in all the major cities served by the Bell System. In 1937, there were over 2 million phone lines served by panel. And even though other systems came along in the 30s and 40s, panel was still growing. And by the 1950s, there were over 3.5 million lines served by the panel system. So whereas a Stroger switch basically could access 1 out of 100 contacts, a panel switch could access, depending on the configuration, 1 out of 400 or 500 contacts, which is much better for a large urban environment. Now, because of the way that it was organized, the panel switch is not directly operated by dial pulses like we saw with step-by-step. You still dial the number, but basically there were circuits that registered the numbers that you dialed and then translated that into controlling the panel switch to make the appropriate connection. And this was intended to be fast, and the motions were larger than in the step-by-step system. So this is actually a motor-driven telephone switch. Along the bottom of the switch, the panel switch frames here, there were electric motors, a drive shaft that ran all the way across, clutches, friction drive rollers, and all kinds of stuff, which made for a very fast operation and ultimately a maintenance headache with this type of mechanical devices as time went on. So here's a panel switch that you can see, panel switch frame, and there are 5 banks of contacts. Each bank has 100 sets of contacts, and they go all the way across the frame. So that's 500 contacts accessible here in 5 banks. And in front of the contact banks, there are vertical rods. These are selector rods, and there are 30 of them across. So the idea is that well, let's look at the next photo. Okay, here we go. Here we can see the panel switch frame, the selector rods, and on each selector rod, there is a mechanism called a brush mechanism that could basically wipe over all of these contacts as it went up and down and make the connections. So there were 5 banks of contacts. There were 5 brush mechanisms, one in front of each bank of contacts. And the idea is that to make a selection of 1 out of 500 contacts for a given selector rod, first 1 out of the 5 brushes would trip so that its fingers would be in contact with the contact bank behind. And then the rod would move up under motor drive, and that brush would contact 1 out of 100 contacts and make the actual selection. Interesting thing is that this stuff was big. Panel frames were 14 feet tall. If we go back to this photo, you can see the fellow here. You can see these switch frames were 14 feet tall. Panel introduced the concept of common control, which was that the switches didn't have intelligence in and of themselves. You dial a number, a circuit registered the number you dialed, the circuit figured out what the connection was that needed to be made through the switch, and caused the switches to move to make that connection that was needed. And then that particular circuit, which is called a sender, was then released and could go do that for another call that was in progress. The other important thing about the panel office was, since it was intended for urban areas, in a city, you were just as likely to be dialing a phone call to a different phone exchange as you were to your own phone exchange. So the panel office was built kind of in 2 halves. There was the originating half and the terminating half of a panel office. And the process of completing a call from an originating office to this office terminating half or some other office's terminating half was exactly the same. So there was no advantage, there was no difference between making an intra-office call and an inter-office call. They all work the same way, and that was appropriate in the urban environment. So we talked about the mechanism here, the brushes that made contact. The switches did know something about the sequence of events taking place to make a connection. Associated with each selector rod, there's a thing called a sequence switch, which is basically like we think of as a finite state machine in computing. What state are we in terms of making the selection in the switch, and what do we do next with that? So that's the panel switch. We have stages of switching in a panel office, just as we had in the step-by-step office. We've got the calling line, it's got its line relay. We have a line finder, just as we had a line finder in step-by-step, but a line finder switch in panel could access 400 lines, basically 10 groups of 40 lines each, as opposed to 100 lines in step-by-step. And now the element of common controls comes into place here. Subscriber goes off hook. and the line finder control circuit has a line finder move up to find the calling line. We connect that line to the most important thing in a panel office, the intelligence in a unit called the register sender. The register sender gives dial tone to the calling line. And now as the calling telephone begins to dial, the register sender is registering the dial pulses and remembering the number that the caller is dialing. The important thing is we dial the first 3 digits, which is the exchange code. And now the office needs to find out how to route the call to that called exchange. So it grabs a circuit called a decoder that looks at the first 3 digits of the called number and basically returns to the register sender the path through these 2 switching frames, the district frame and the office frame. And these are panel switch selectors, analogous to selectors in the step-by-step office, and eventually routes the call to an inter-office trunk that will take it to the appropriate terminating office. So the information that the decoder returns to the register sender is going to the selector, the district office frame, what brush to trip, and what group of contacts to look for within that brush's contact bank. That'll get it to the appropriate office frame, where again, you trip the appropriate brush and you move up to a trunk group that'll get you to the desired terminating office. So there's basically, the key thing here is that there's no relationship between the physical layout of the office and the exchange code that was dialed. Whereas in step-by-step, the physical layout of the office, or the switches in the office, is directly related to the telephone number. They're inextricably linked. Here you have this decoding function, which means that trunks to the appropriate terminating office can be placed anywhere within the switches, and the information in the decoder will enable the register sender to make that connection. It's very interesting the way these switches actually work. As I said, the switches are motor driven, and so they're moving up across a bank of contacts. At the top of that switch frame, there's a device called a commutator rod that moves up. Well, it's attached to the selector rod. And every time the switch moves up past another contact, that commutator generates a pulse. And that pulse basically goes back to the register sender, which counts the pulses. So the way a panel switch gets to the correct position is as the selector rod is moving up and the brush is moving across the contacts, pulses are coming back to the register center, which basically counts down and says stop when the panel switch gets to the right contact. So different from step-by-step, where the telephone dial causes the Stroger switch to move up. In panel, it's motor driven. The switch is sending pulses back to the register sender that counts them and says stop. The technique is called revertive pulsing. The same thing happens when we reach the terminating office. In the terminating office now, we're just trying to get a 1 out of 10,000 selection. Unlike the layout of the originating office, where we're going all different places, all different terminating offices, the layout in every terminating office is the same, because we're just trying to get to the right 1 out of 10,000 lines. So the telephone number that's desired will tell the register sender exactly how to route the call through the frames of the terminating office in terms of the brush selection and the group selection in the incoming frame. And then, just as in a connector in a step-by-step office, the final frame gets you to the last 2 digits of the telephone number that's dialed. And then we ring the called line, and we've got our talking connection. Once the talking connection is established, the register sender drops off and is now free to do the same thing for another call. So this very complex circuit of the register sender is occupied for the 12 to 15 seconds that it takes to dial a 7-digit number and actually set up the call. Okay, let's go through another video that shows how this is done. Yes.
Yeah. You've indicated that there are various memories in this system. Could you talk a little bit more about what those consisted of?
It's all relays, basically relay contacts that are closing and being held to retain that information. For example, to count dial pulses, to figure out a digit, to register a digit, there's actually a relay counting circuit, and the digit is then stored in what's referred to as a 2 out of 5 code. There are 5 relays in a group, and 2 out of those 5 relays will operate, and which 2 out of the 5 operate indicate the value of the digit. So basically you would have 7 sets of these for the 7 digits of the telephone number that are being dialed. So the first 3 digits will be dialed. The register sender will grab it front to the terminating office, and that takes a couple of seconds. And while that's happening, you're dialing the last 4 digits of your number. And once all those 4 digits have been registered, the call gets completed to the terminating office. But it's all relays. The decoder is basically a big field of wires that are interconnected. That you present the digit information, and then other relays in the register sender sense the pattern of connections that correspond to the digits of that office code comes back as the brush and group selections for the panel switches. So again, relays close and hold that information for this call. So it's all relay contact closures throughout the whole system essentially. And the panel switches have rotary sequence switches that basically tell them what the next step in their operation, the operation of the individual switch should be. I'm going to show another video that shows how the panel system actually works. This is an excerpt from a incredibly excruciatingly detailed half-hour video on how a panel exchange works. And it's done by a group out in Seattle called the Connection Museum, where they actually have working telephone switches from this era. And it's a very well done video. The guy who's doing the person who's doing the video basically is very intent on showing you what the sounds are that you might hear on a telephone line as a call is being completed, and they do that by actually recording right off the wires of the phone line, the clicks and pops and so on and so forth. And so he's showing some of that, and then showing you how the individual switches move. And so we'll take a look at that at this time. Okay, so here we go. Remember, this is basically the review at the end of a half-hour video.
Pick up were attached to a sender and also moved to the quiet talk battery. The sender gives us dial tone to indicate it's ready to receive digits. We dial 722, noting that the dial tone is not removed from the line until after the A-digit register is locked in the sender. Immediately after we do that, in only 1/3 of a second, the sender asks the decoder what to do with that office code. We don't hear this on the call, even though it's very important. Instead, we just hear the sender beginning to make district selections. First, we move the district sequence switch. Then we go up 0, 1 to our district brush. Then we move the sequence switch again, engage the trip rod, and move the sequence switch again for district group. Once we've locked in our district group selections, we dial a 5 and make our incoming brush selections. Sequence switch, incoming brush, sequence switch, ready to trip. Dial a 6, and we get incoming group. Sequence switch again, and now we have the final brush as well. One more sequence switch movement on the final frame to get that trip finger ready for the upward movement of the rod. And then we dial a 7. Sequence switch moves for final 10 selections, and we count up 8 pulses to the 7th group of 10s. Finally, we dial an 8. The sequence switch moves, and we count 9 pulses to get to the 8th units terminal. After we reach the terminal on the final frame, the call is all set to go. We just need to signal back to the sender that we're ready and incoming advance. That tells the sender to go ahead and move the district sequence switch into the talking position, which cuts through the voice path between the calling and called parties. Now, we'll wait a moment for that ring cycle to line up where we want it, and there, we're ringing the phone. So that's it. That's a call from a panel office to a panel office.
Any questions
Ken?
about the
Yeah,
panel?
I'm kind
before we go on?
I'm kind of curious about how it interoperates with the other kind of switching. So if you have the two different switches on other sides of the trunk, how does that
Right.
how does that work?
Yeah, that was not a problem that the Bell system was originally trying to solve with panel, because they basically wanted to saturate their their urban areas with panel, and if you were dialing outside your immediate area, you needed to get the assistance of an operator. Stuff was retrofitted, obviously, to panel offices as time went on. I remember it was the late 60s, I think, in Cambridge when I was at MIT, that with great fanfare, New England Telephone introduced touchtone dialing in Cambridge, where there were still panel offices. So basically, there are additional types of trunk circuits needed to be added to the panel offices. But keep that thought in mind, because you'll see something interesting that happens when we go to the next generation of switching systems after panel. I'm looking at the clock, and I've got 2 more systems to cover, and only a half hour to do it. So let's move along. Drawbacks and limitations of panel. The scope, the size of the panel machinery basically gave it the large scalability that the Bell system was looking for, but it was rotating machinery, required cleaning and lubrication and adjustments, lots of finicky adjustments. If a couple of contacts, those wipers got misaligned, you could wind up completing a call to the wrong number. Even though the switch did all the right things, it was just off by a little bit, and it contacted the wrong line. The contacts and the wipers were brass, and there was actually wiping. The metal contacts were wiping across one another. Panel offices were notorious for noisy phone connections, lots of crackling sound as the contacts tarnished and wore and created electrical issues. And I know that certainly in Boston and Cambridge, it was pretty well known back in the 60s that in the panel offices, sometimes you'd place a call and it would go nowhere. You would just get nothing. The switch wouldn't complete the call. So even though a lot of panel was installed on the Bell system, the Bell system worked on developing newer switching systems than that. The interesting thing was that telephone switching systems, electromechanical switching systems, were designed for a 40-year lifetime. And most of these went in the 1920s and some of them in the 1930s. And when the Bell system began developing electronic switching, first ESS went into service in 1965. The idea was to quickly ramp up and replace all of those aging panel systems that were becoming very difficult to maintain. Turns out that that didn't happen, because in the 1960s, when ESS was first deployed, there was burgeoning demand for telephone service. So most of the production of ESS, even installed in large cities, were used for new service, for new central offices. And it really took until into the mid 70s and even later for there to be enough ESS deployed to be able to retire all of the old panel systems. I was a student in Cambridge, and so I was pretty familiar with what was in Cambridge. For those of you who are familiar with the area, the 354 and 547 offices in Cambridge were panel, Elliott and Kirkland. So on to the crossbar switch. We're trying to overcome some limitations of panel, and research in Bell Labs in the 19-teens came up with some ideas, a couple of patents, but they didn't really pursue it from an engineering perspective. The work was picked up in Sweden, And the Swedes actually developed a switching system based on the crossbar switch in 1926. When Bell Labs was looking around for something better than panel in the late 1920s, they went back to the crossbar switch and used that as the basis for a new common control system that became known as number one crossbar. So here's a diagram of a crossbar switch, and basically it consists of 5 horizontal bars, which are called selecting bars, and depending upon the size of the switch, either 10 or 20 vertical bars referred to as hold bars. Each of these could be operated by magnets, and there's basically a small motion. The bar would just swing a little bit. The horizontal bars could swing in either of 2 directions, depending upon which magnet was operated. So it gave you a 1 out of 10 selection on the horizontal dimension of the switch. And then each hold bar, of course, gave you a 1 out of 10 selection or 1 out of 20 selection in the vertical side of the switch. So you basically had a matrix of potential connections that could be made in the crossbar switch. Very small motion to operate, so you didn't have the problems of the mechanics of a panel switch. And also, unlike step-by-step in panel, where one selector could make one connection at a time, in a crossbar switch, you can close multiple cross points at a time. So you could have 10 connections going on in a crossbar switch at one time. So it's very efficient in its use of space. Here's a little bit of a diagram of how a crossbar switch works. Here's the select bar, and you can see this little finger in its normal position. It's in between these 2 sets of contacts here. If you operated the magnet, the bar would move just a little bit. The selecting finger would go down to either of these 2 dotted line positions. And then when the hold magnet was operated, that hold bar would rotate, and the selecting finger would push the cause of the 2 contacts to be pushed together, making the connection. And so then at that point, the select magnet could be released, and the hold magnet would continue to be operated, and that would maintain the connection that was made at that cross point. One advantage of the crossbar switch, and not only the crossbar switch itself, but all of the relays in the crossbar office, was that they started making the switch contacts plated with precious metal, so that they would eliminate the problem of noisy contacts and intermittent contacts that you had with the brass contacts in the panel switch. So here's the number one crossbar system, a photograph of a central office, and a close-up of switch frames in number one crossbar. First deployed in 1938, and it was specifically designed to interoperate with panel offices. There was panel throughout the Bell system, and they said, we're going to add number one crossbar as an alternative to panel, but it's got to fit in seamlessly with panel. So number one crossbar retained the originating office, terminating office distinction that we saw in the panel offices. And the interesting thing was, even though the revertive pulsing that was used to communicate between the terminating office and the originating office and panel was tied to the operation of the panel switches and the way that they worked. The Bell system, basically in number one crossbar, still used revertive pulsing as the means of communicating between the originating office and the terminating office in number one crossbar. Had nothing to do with the operation of crossbar switches, but revertive pulsing was now used just as a signaling mechanism. And one video that I was looking at suggested this is an early version of a protocol, an abstract protocol. Had nothing to do with the underlying mechanism, but everything to do with just the signaling mode that you wanted to use. So crossbar overcame a lot of the objections to panel. There are no motors, there are no large motion parts going on. There are no wiping contacts because we had the precious metal relay and switch contacts. And as you'll see, there's much faster call setup in number one crossbar than in panel. The crossbar switches themselves just make connections. There's no intelligence at all in them. They're none of the sequence switches that told the panel switch what to do next. We still had senders to register dialed digits or to register digits sent between the originating office and the terminating office. What we had instead of what we have for intelligence and decision making in a number one crossbar office is a very large relay device called a marker, so called because it marked the path that was to be established through the crossbar switches, marked it with electrical signals, of course. And markers work very rapidly. They take a half a second to a second to actually establish a path through the switch. And so you could have a 10,000, 20,000, 30,000 line office with only a few markers because they're constantly going from one call to the next to establish the call. So here's a diagram of a number one crossbar office. Our line finder frame of a step-by-step and panels replaced by a line link frame. And basically when a phone goes off hook, that's, again, we have a line circuit that signals the request for service. A connection is completed to an originating sender through several switch frames here. The originating sender returns dial tone to the customer dials the number. And now the sender has registered all the information from the dialed number. It finds an available originating marker. The marker takes that information from the sender and says, okay, I know how to establish that call. And that's going to this other central office over here. Here's an appropriate path through the district link frame and the office link frame. And ka-chunk, the marker operates the crossbar switches to establish that path. Now we've got a connection to an incoming trunk at the terminating office. And again, we go through some switch frames to a terminating sender. And now the interesting thing is the terminating sender has to impersonate a panel office. So it's got to go through the same steps that you would go through in a panel office in the terminating half of a panel office. And so it sends the same kind of pulses back to the originating sender that a panel office selector switch would, the brush selection, the group selection, and so forth. And in the same way as in the panel office, the originating sender is counting those pulses and saying stop. And when the originating sender says stop, the terminating sender says, aha, I know what the number is that's being requested here. So the last 4 digits are dialed and registered in the terminating sender. The terminating sender then grabs a terminating marker, which establishes the path through the incoming link frame and the line link frame to the called customer's telephone, which then rings the called customer's phone. Interesting thing is that in both step-by-step and panel, the line finder and the connector or final frame in panel are two completely separate different structures, two completely separate different things. In the number one crossbar office, these line link frames, the originating line link frame and the terminating line link frame, are identical and in fact shared between the originating half office and the terminating half office because it's just a matrix of connections through the crossbars. Connections can go in either direction. So again, I'm going to jump into a video, and like the other one from the Connections Museum, this is going to be the review section of a half-hour long explanation of how number one crossbar works. And so there'll be a couple of remarks tying back to the earlier explanation, but you'll get a feeling for how a call goes in number one crossbar.
We connect to an idle originating sender, which gives us dial tone. As we begin to dial, we note that the dial tone continues through the A digit, which is a peculiarity of these old-style crossbar and panel senders.
You'll see a different kind of memory for storing the digits here.
After 3 digits are dialed, the sender bids for an originating marker, which decodes the office code 833 and returns information back to the sender regarding how to complete this call. The marker also looks at the office link frame and locates the trunks to our called office. It then observes the state of the district link and the office link and builds a connection from our district junctor through to the outgoing trunk. Once it's done this, the marker disconnects itself to be used on another call. Now, we're back to the sender. As we continue dialing, nothing much happens until we get to the hundreds digit. At that point, our sender closes the connection over the trunk to the terminating office. This wakes up the incoming trunk in the terminating end, and it immediately bids for access to a terminating sender. As soon as the terminating sender is connected to the line, it begins pulsing at us. Lucky for us, we were ready for it, and as soon as the pulses start to come in, our originating sender starts counting them. Here, the terminating sender is pretending to be a panel selector, and as it pulses, we're counting off incoming brush, incoming group, and final brush. Each time we're satisfied, our originating sender opens the trunk loop, which tells the terminating sender to go ahead and store the number of pulses that it sent us in its crossbar register. We dial our tens digit, it pulses again for final tens. We open the loop, it registers, and now it's time to dial that units digit. Immediately after dialing the units digit, our originating sender does something important. It needs to make one last check to make sure of what party we are, in case we're on party line service. Recall that it did this when we first started our call, but we just didn't hear it. It disconnects us from the dialing loop, does its test, and then reconnects us. As soon as it's satisfied, it closes the trunk again to the terminating sender, which has been waiting for us so it can send its revertive pulses for the units digit. As soon as that's done, the terminating sender transmits a polarity reversal back to us, which we interpret as incoming advance. That instructs the originating sender to drop off a call and cut our district junctor through to the talking position. Now, we're hanging out on the trunk and waiting for the terminating end to complete its work, which is actually happening simultaneously with all of this. On the far end of the call, the terminating sender transmits the last 4 digits of the called number to the terminating marker. The marker then calls up its friends, the number group connector and block relay frame, and gains access to test the called line. Now, it tests that line for busy, and if it's available, the terminating marker proceeds to set up our connection from the incoming trunk through the incoming link and out to the line link where that called line is located. Once it's done that, the marker disconnects and makes itself available to serve another call. Now, our incoming trunk rings the called party, who will, one of these days, hopefully, get around to answering us. Well, that's it. That's your standard crossbar to crossbar call. But it's only the tip of the iceberg if we're talking about all the things the number one crossbar can do.
And that was a demonstration of number one crossbar. There's a question about memory before. As you can see in the number one crossbar, it actually stored the number that was registered in a crossbar switch rather than in a bunch of relay circuits. So that was an interesting concept there as well. Okay. There's lots of number one crossbar that was deployed in the Boston area. Again, I was kind of familiar with Cambridge. So the 864 and 868 and Trowbridge exchanges, 876 exchanges in Cambridge were original number one crossbar. And late in the process, after they stopped assigning names to phone exchanges, the 491 exchange in Cambridge was also number one crossbar. I think we're running out of time to cover number 5 crossbar, which is probably the most sophisticated crossbar switching.
Ken,
yes.
With regards to time, generally what we've noticed in the last few months is that if you have more stuff to do and you want to do it, fine. If somebody's got to log off, they log off. But
Okay.
it doesn't matter if we go over, because it's not as if we're going to be kicked out of the room.
Okay. All right. Well, then I'll plug on here.
Okay.
And for those who can stick it out through, we probably got another 10 or 15 minutes here, 20 minutes probably. At the end, I've got a little lighthearted video that I'd like to show. So hopefully you can stick around for that as well. All right. Let's go on then to number 5 crossbar. Thanks, John. So number 5 crossbar. Number 1 crossbar, again, was designed for the urban area to interoperate with panel. But there is a need, especially as the suburbs began growing after World War II, for another type of crossbar office. The Bell system did not want to keep deploying step by step. It was not particularly efficient. Crossbar was seen as the future of telephone switching, and so the number 5 crossbar office was developed. Unlike number 1, the number 5 crossbar office did not have originating and terminating halves. It was all just one office. The question was asked before, what do you do about communicating with other types of switching offices? That was explicitly designed into number 5 crossbar. There were trunk circuits that were designed to connect to step-by-step, to panel and number 1 crossbar, to long distance using multi-frequency signaling, and so forth. The design of the office made it easy in the 1960s to add touch-tone dialing into the originating register of a number 5 crossbar office. And certainly one important thing was that a number 5 crossbar office could handle any number of dialing plans. You could put into a small location where people are still used to dialing 4 digits. You could put it into an environment where you're going to be able to do direct distance dialing, and it could handle 11 digits. And that could all be incorporated into the design of the office. It's also the first switching office that could do automatic call billing, basically by punching a paper tape with call detail information about a call it was going through. It also had a punched card trouble recorder, so that if something went wrong and a checking circuit discovered that something went wrong, it would punch a big large format card. So the office could be unattended at night or on weekends, and somebody could come in the morning and look at what the troubles were that occurred in the switching office over the night before. So number 5 crossbar went in starting in 1948 at Media, Pennsylvania. And as I said, there was only one kind of office in number 5 crossbar. It handled both originating and terminating. There was just one type of marker instead of the originating marker and terminating marker in number 1 crossbar. The number 5 crossbar marker is said to be the most complex relay circuit ever designed. It had over 1,500 relays that were involved in completing a call, and it was really a CPU in relays, if you will, and it performed a call setup in a half second, basically. And there would be some number of markers in a crossbar office, depending upon the size of the office, maybe 3 in a 10,000 line crossbar office, or a dozen or so in a 50,000 line crossbar office. Talked about message accounting and trouble recording. Oh yeah, Bell Labs patented the number 5 crossbar office in one patent, and it is said to be the largest patent ever issued by the US Patent Office. I couldn't find any reference to that, but I was told this by people at Bell Labs back when I was there as a college student. So here's the number 5 crossbar office.
And before we go there, just one quick question, just to go backwards.
Sure.
How was the billing system handled in the old system? You alluded to this in the new system, that it's on tape. What do they do in the old days?
Okay, well, in the old days, if you wanted to make a toll call, you had to go through an operator. So the things that you could dial were all local calls. And I skipped over this in the presentation, but if you go back and look at these videos, you will see that both all the offices, step-by-step panel and number 1 crossbar, basically had little counters. So when you went off hook and made a call and that call was answered, a little meter clicked up one, a little counter. And every month, clerks would go into the office and read all the meters associated with every telephone line in the office and write down how many calls were made, and that's how they would bill you. I think a little bit later on, there's the concept of some calls cost more message units than other calls. And I guess, they had to increment the meter 3 times for a 3 message unit call, something like that. But that was basically it. Anything that was a toll call went through an operator at the time. So, okay. Much simpler in form than the number 1 crossbar office. Basically, there's only one switch network, line link frames, trunk link frames, and outgoing trunks. So basically, the same switch network was used for outgoing calls to other offices, for incoming calls from other offices, and also for intra-office calls, where you would go from a customer line on a line link frame through to a trunk. That trunk would actually have 2 appearances on the trunk link frame because it was an intra-office trunk, and you'd have another connection going back through the trunk link and line link frames to the called party. The same switch network was used to connect the customer line to the originating register to get dial tone and to register the digits. As I said, there's a sort of a variable, you can have a variable number of digits required to make a call. So typically what would happen in number 5 crossbar is when you dial the first 3 digits of your call, the originating register would query a thing called a pre-translator with the 3 digits that you dialed, and the pre-translator would tell the originating register how many digits should now be expected following those 3 digits, so that the originating register would collect the correct number of digits from the caller. And when it had all of the digits, the originating register would grab a marker, an idle marker, pass the marker all of those digits, basically, relays with lots and lots of contacts, passing that information onto the marker. The marker would look at its translation, which again is a bunch of interconnected wires showing it how to complete that call, and then find an idle path through the switch frame and set up that call. And so the marker was involved twice in setting up the call. Once to connect the calling line to dial tone, and then after the dialing had been completed, a second time to set up the desired call, outgoing or incoming or intra-office. If it's an outgoing call, the marker would pass the information, the dialed number information to send out on the trunk to an outgoing sender, and that would then outpulse or however send the information out on the trunk to the other office. For an incoming call from another office, that call would come in and be connected to an incoming register that would receive the information, the number information, and the incoming register now would grab a marker to complete the call to the called line in this office. So that is a quick explanation of how call setup went in number 5 crossbar. I'm going to skip over these individual slides. You can look at them later if you'd like to get individual dial tone connection, outgoing trunk connection, incoming trunk connection, and intra-office connections, basically a more detailed explanation of what I just went through. And I'd like to do another video about number 5 crossbar. This one's a little bit different. There isn't a detailed explanation, step-by-step video like we had for panel and number 1 crossbar. This is in the same outfit. It's the Connections Museum in Seattle. But what we have here is a technician who actually worked on number 5 crossbar, giving a tour of the number 5 crossbar office to a small group of people, and that tour was recorded. So you'll see an explanation of the different frames and so forth, but we won't have this detailed step-by-step explanation of call setup.
The crossbar switch is the single unit switch that makes the system unique. And if you look closely, you'll see there's 5 horizontal bars and there are 20 vertical bars. Each bar that's horizontal can be moved up or down depending on which one of these magnets is engaged. Okay? And as it moves up and down, you'll see that there are these tiny metal fingers that are behind the bar. And each metal finger can either be positioned on the top switch or positioned on the bottom switch. Then the second part of the operation, once that selection has occurred, is what we call the select magnet, which then pushes that finger into the switching place. So there are a total of 200 possible cross points on one switch that can be operated. But the point I'm going to make here, and the really important thing to consider is, remember the step-by-step system and all the ratchets and moving parts. Remember the panel system and the pulleys and the sequence switches and everything moving all over the place. To make a connection on the crossbar switch is like this. Done. Select magnet and hold magnet done. That's how fast it is. Way fewer moving parts. Okay? You can see where this was a tremendous advantage in terms of maintenance and reliability over the earlier system. Now, in reality, of course, you can consider this as one huge, enormous matrix. Okay? These switches were in fact paralleled together in various subframes to make the system work. But to simplify it a bit, think about this being this vast matrix of connection points, thousands and thousands and thousands and thousands of them. Your telephone is up here. The number you're calling is in that matrix is way down here. Okay? What this machine has to do is identify where you are in the whole system, identify the number you're calling and where it is, and then to analyze that entire matrix to find out which pathways are already in use by the callers and which ones are free, and then to actually plot a route for the entire system to get from where your phone is to the number you're calling. And then once it's made that analysis, plotted that course, then it sends a signal to operate all these magnets simultaneously to connect your call. That whole process occurs about that fast. Okay?
If it's not working, it must have been out of charge.
Oh, that's an even more amazing part, which we'll get to in a few minutes. Let's first of all, I'm just going to hook this up so you can kind of get a feel for what it actually sounded like when it was operating. This little gadget here is nothing but an automatic dialing machine that dials random numbers into the system. Okay, so you can watch it here soon. And this, believe it or not, and I've actually gone through working off this pipe. And they were much lighter than this. This is just a few calls going through. So this might be what an office sounded like at midnight or something like that. There wouldn't be much going on. So let's take a closer look at some of the subunits. See how this works. Let's go around this way.
Don't mind me, guys.
This bank of equipment was comprised of what are called originating registers, or ORs, and these are the devices that count and store the telephone number that you dial. So you can see these little relays sliding around. They're busy counting each number you dial. Once they count the number you dial, they store it in this little read relay pad. Okay? And they count the next number that you dial and store it. Count the next number you dial and store it. Until you've completed dialing your entire telephone number. Then send that information simultaneously to a device called the marker, which is the central processor in this system. Once it's done that, it's done. Collected the dialing information, send it to the market, now it says, I'm ready for the next call. Another call comes through, it does exactly the same thing. And that's all it does, all day long, it just repeats, collect the information, send it. Count it up, send it. That's all it does. So just as in the panel system before, this uses the concept of common control, where you use a single piece of equipment to share that amongst the others.
These relays are kind of unlike any other kind of relay I've ever seen.
These are called wire spring relays.
Yeah.
And they're probably the best advance that they made in relay technology. They were relatively simple to manufacture. And each one can be configured independently by flipping off which contacts are going to be used. And they could also kind of decide what order these things dispose by the way that the card here was configured. So it was possible to take the same basic motor and make a bazillion different kinds
Lots of poles on them, yeah, really amazing.
Yeah. The connector relays like you see over there are even larger. So here again, one binary switching circuit, one input and almost unlimited possibility of outputs for any given switch. So next we're going to head over to the marker. Okay. So this whole section of 3 frames here is called a marker. It's the equivalent of a central processor for running the processor. Every time you hear that chorus of relays, that's a call being computed. Another one. Okay? Another one. There's another marker behind this, a newer version. So remember again, what this is having to do is having to identify the call number, identify the calling number, check that entire vast matrix for what circuits are there available, plot a course, and then operate all the magnets. Okay? And one marker contains roughly 1,500 zeros. Without question, one of the most complicated relay devices ever devised. Okay? So that you can see the advantage is that you can use that one, and of course is one call. And then once it's done, it's dropped off, it's ready for the next call. So this can process many, many calls, as you can see. So a small suburban central office might have maybe 3 to 6 markers for the thousands of numbers that it serves. So there's only the calls being made that we have to deal with. Right, the only time it was operating was in establishing the connection, and then it was done, and then it was moved on to the next. Sounds like music to me.
Back to the
that was the best line. It sounds like music to me. That was excellent.
Yeah, that one's fun.
It also sounds very much like a router that we have today in the internet. The basic concept hasn't changed very much.
Yeah, and signaling protocols and all that sort of stuff. So in the Boston area, after World War II, there's an extensive deployment of number 5 crossbar. When I moved to Lexington in 1980, and the Lexington central office was number 5 crossbar. The original central office code in Lexington was volunteer 2, otherwise known as 862. That got added on to with 863 and 861. The 492 exchange in Cambridge was number 5 crossbar. And I think a number of the offices in the sort of the outskirts of Boston, the city of Boston, were number 5 crossbar. I think the first number 5 crossbar office in the Boston area was Belmont, and one of the newest ones was in Wellesley, I believe. So very extensive deployment of number 5 crossbar, and it became actually. The Bell system licensed the number 5 crossbar technology and was deployed extensively in Europe by other manufacturers as well. I'd like to close, I'll take questions in a couple of minutes. I'd like to close with a somewhat lighter note, which is about the term cutover. And if you've ever you've all been involved in cutting over a system, if you've ever wondered where the term cutover comes from, you may find it resolved by looking at this. Here we go. I think you'll enjoy this. 1984.
The Place, a Pacific Telephone Central office in Glendale, California. One of the oldest functioning switches in the nation, a 35,000-line step-by-step office, is going to be transferred to an expanded ESS facility. Western Electric's speedy cutover service was selected by Pacific Telephone to provide a fast, reliable, and economical transition from the old to the new system. Features of the service are explained by Western Electric account representative Rick Snowden.
Speedy cutover service is a method by which installers come into the office to be transitioned from step or crossbar to ESS and actually perform the physical cut of the old office away from the new office. The out of service time is just a matter of seconds as compared to previous methods that took minutes and even up to an hour in some cases. Several installers come to the office maybe a month before the cut, and they analyze the cables to be cut and perform continuity tests to verify, to make sure that they have the exact cables and move them away from other existing equipment. After they're identified, they're tagged so that on the night of cut it can be a clean operation and nothing else gets cut.
For this cut, 127 feet of scaffolding has to be erected the day before to accommodate the installers cutting the cables on the upper portion of the intermediate distributing frame. On the evening of the cutover, 51 installers and 3 supervisors are assigned to cut the 927 cables. Western Electric Supervisor Gary Brannon briefs them.
There's approximately 20 cables per person. These cable cutters are sharpened in a special manner so they will cut a clean cut through these and not cause any shorts.
Following a short rehearsal, the Western Electric installers wait with cutters ready. 3 floors above the IDF frame, Pacific Telephone people are hooked up to the cut supervisor and TSPS operator who is handling emergency calls.
I will be on that conference line approximately 1 minute before 11. They will give us the order to cut as soon as all emergency lines are down.
Mary Ellen, would you call the operator? Make sure there's no emergency calls in progress, please.
Hi, this is Mary Ellen at Glendale 11 CGO. Have you got any emergency calls in progress at this time? Good enough. It's all clear, Don.
Okay, Western, cut the cable.
Cut it! Let's cut it! Okay, cut complete.
It's cut.
Nice cut, Western, 47 seconds.
Western Electric's speedy cutover service, an economical, dependable, quick response to telephone company needs.
Well,
I think that Scott
after that
Adams,
video, I'll never think about the term cutover in the same way again.
I think that Scott Adams worked for Pacific Telephone. The guy that wrote Dilbert.
Okay.
So what do they do with the old cables?
Dilbert cartoons coming out of that video.
What happens to the old cable?
Well, after, there's a lot of cleanup to be done afterwards. I think the basic idea is, you've got the all of the cables coming in from the outside plant into the distributing frame, and originally all of those cables were tied into the old step-by-step office, and basically, they connected on top of those cables, the cables going to the new electronic switching system. So it basically connected together, but the electronic switching system wasn't enabled, so there was nothing, on those wires. They cut all the existing cables to step by step, and then essentially activated the electronic switching system. that reactivated all its lines. So basically, you know, nobody in Glendale can make a phone call for 47 seconds.
Yeah, but I was looking at all that nice plastic insulation on the cable, and you know, and wondering what happens to the copper inside the cable. And back then, were they doing any serious recycling?
And gold contacts.
No idea. No idea. So
Ken, thank you very much for a wonderful presentation.
Well, you're welcome. I'd be happy to hang on for any questions that people might have, or, you know, we can.
And please thank your wife and tell her that we'll schedule you again after you can get a breath of air.
All right. Glad you enjoyed it.
So they took reliability very importantly back then. And the design life of a switching system, as Ken said, was 40 years. And I think for ESS1, they only allowed 2 hours of the thing being out over its 40-year life, which
That's
is,
right.
you know, it could be partial parts out, but not the whole thing had to be up and ready no more than 2 hours out in 40 years, which is a pretty high design level.
My first co-op assignment at Bell Labs was working in a switching department, and they were developing a thing called the automatic intercept system. And I learned about some of the reliability principles in their design. And one of the things that they taught was, you know, in a business computer, the thing that's really important is the accuracy of the computations that are being made. It's okay if the system crashes once in a while, but you don't want it to make a mistake in a calculation and keep on going, because you never find that. Whereas the opposite was true in a computer-controlled telephone switching system. It's never okay for the system to totally crash. But you know, if you lose a call once in a while, that's not so bad, as long as the system recovers and keeps going.
You know, that's like a human.
Yeah. Yeah, they actually designed what they refer to as software audit programs that basically, you know, understood what the layout of the data structures was in the memory of the computer system, and on a regular basis would kind of examine those data structures to make sure they were all consistent in the way they were supposed to be. And the job that I had that summer was designing the structure of audit programs for the automatic intercept system. Actually devised a scheme that they were astonished that this MIT sophomore came up with, and they used it, which is, you know, amazing. Anyway, yeah, so that's what they did then. Another question.
And has this history been written? Are there books about this, about the people and
there's
process?
There's a book I think it was in the 70s. That was the primary author was Amos Joel, who was the executive director of switching at Bell Laboratories for a number of years. I think his name is on the number 5 crossbar patent, something like a history of telephone switching in the Bell system. Whether that's available anywhere, I have no idea. But I had fun browsing the web and coming up with, I thought the Connections Museum in Seattle was a great find. You know, AT&T has an archives website that has a YouTube channel with a whole bunch of videos on them. Some of them much more promotional in nature, the ones that I use today.
Well, the oral history is pretty awesome. So thank you very much for the personal.
Yeah, I had a book. This is a book that I bought back in the 70s, Basic Telephone Switching Systems, and it basically goes through, you know, it's the explanation of stuff that I talked about here. It doesn't mention number 1 crossbar really, but it does step by step in panel and number 5 and the principles of switching in more detail. More stuff about circuits, individual circuits and individual telephone switches and how they worked. I think you can still find this on Amazon as a used book. You know, if you're interested. And you can go back to the Connections Museum in Seattle, look at their YouTube channel, and watch the full half-hour video on number 1 crossbar and panel. And they've got some others. You know, they've got one video where somebody is making very fine adjustments in a panel selector switch because it's not working quite right. and talking about the same kinds of things that technicians in those days were doing. It's you can really get into this and waste a lot of time on it.
Ken, I have a quick question. One thing I'm missing here in the switching systems, it seems to me that when the first 3 digits go in, something happens in the switching system, and then the rest of the digits are put in. Why is it that the first 3 digits cause something to happen? Is something in information technology that is going on there?
It's that's true in panel and number 5 crossbar. If we started step by step, basically every time you dial a digit, something happens, right? The system progresses from one selector to the next, and then through the 2 digits of the connector and step by step. So that's called progressive control. Every digit causes something to happen. In going to common control in panel and crossbar, you're basically deciding what to do at the appropriate time. So the way panel and number 1 crossbar are arranged, you've got the originating office and the terminating office. The first thing you need to know is, what terminating office do I want to connect to? So that's the first 3 digits, right? You're dialing the 3 digits of the office code. So in panel and number 1 crossbar, you dial the 3 digits, and then the system figures out how to route to that terminating office that you want. So that's what they're going to do. That's what it's going to do for you. Then, but you as the subscriber are free to keep dialing. In the demo videos that we saw, they're just basically showing each step of the way as the piece of equipment gets ready for the next step. You could be dialing all of the digits, and you might be a digit or so ahead of the equipment setup that's going on behind the scenes. In number 5 crossbar, as I said, after the first 3 digits, the originating register wants to know how many digits to expect, based on what did you dial an area code, and therefore you're going to be dialing 10 digits, or did you dial 1 plus? So you're going to be dialing 11 digits altogether, or did you dial a local central office, and so it's only going to be 7 digits, because the originating register needs to know how many digits to register before invoking a marker to make a connection. So the first 2 digits cause a connection to happen in panel and number 1 crossbar, and that's what you're seeing there. Ken?
Yeah, a question about operator assistance.
Mm-hmm.
So in the very early days, there were operators working in these localities.
Right.
And my question for you is, how much training did they require in order to place a long distance call, say to another country? Do they need to know how to do that whole operation, or did they sort of hand it off to somebody higher up in the hierarchy who would know more about the global aspects?
That's actually a good question, and I'm not certain of the answer to that. I think it probably depends, where you were. A truly local operator, if you got a dial 0 operator, that operator would be local, and you would probably say, give me long distance, or give me international, or right, and that would go to an operator that handled those calls. Within an urban area, if you dialed 0, you would get to sort of a centralized operator location where there would be lots of operators. They would probably be more highly trained. And operator distance dialing was introduced a decade before subscriber direct distance dialing was introduced. So you actually had long distance operators. I talked about number 1 crossbar, number 5 crossbar. I think there were 2 abortive crossbar developments of number 2 and number 3. Number 4 crossbar was the long distance toll switching system in AT&T. And one difference between that and the other crossbar systems is that was, we talked about telephone lines are 2 wires. Long distance is 4 wires, because you've got separate paths for transmit and receive. So number 4 crossbar was a 4-wire toll switching system. And the operators who accessed that actually had key sets that generated those multi-frequency pulses that some of us were chatting about before I started the talk. So those operators would have known how to do all of that.
Thank you.
And in fact, if memory serves, if you look at old films, lots of times when somebody wanted to place a long distance call, they would call the operator, say, I wanted to call some country.
Right.
And then they hung up and they gave the number. And at some point in time later, when the line was clear, so to speak, they could get a connection, they were called back and said, your call is ready.
Right. That's right. Yep.
Yeah, that's
Sometimes
right, you guys. Yeah, that's right, you guys, because my late wife comes from Britain, and in 1958, 59, we get married in 63. But anyway, when I called up there, it was an experience, Sometimes you call the international operator, or sometimes you could, I'm not sure if you could dial it directly or not. It's so long ago, I don't remember. But I know it wasn't difficult. But there were times, though, when the overseas lines were busy, especially during the holiday seasons.
Yeah, Bell Labs was very big on human factor studies and all of that sort of thing. And I remember one of my co-op assignments there. I was visited by human factors people who were just basically conducting a study. They were planning on adding instructions for international direct distance dialing, to publish in phone directories. And what they were trying to figure out was what was the simplest way to explain to a subscriber how to dial an international number. And so they basically had a couple of questions, and one of them was, here's a written representation of an international telephone number. If someone told you that this was what you needed, this is the number you wanted to call, what would you actually dial to reach that number with these instructions? And they're trying to see which instructions were the clearest and which would have the fewest errors on the part of users.
Second question, Ken. I'm curious about the alert message. That is what makes the phone ring, and the actual transmission of information when you're talking on the phone. Is there anything different about those two? Because I grew up in a farm.
Okay.
We had a party line, and you had a ring come into that party line.
Right.
And that alerted you that somebody wanted to talk to you or somebody on that party. And then you raised the receiver. The receiver, and then you talked into the microphone. Was there something separate about those two, or are they all together?
Well, it's all coming over the same pair of wires back to the central office. And probably if you were on a farm, you were probably served by a step-by-step office. Yeah. So you saw in the diagram I showed of step-by-step, that's the connector switch that ultimately is handling the details of when the last two digits of the call are dialed, the step-by-step switch advances to that called line and applies ringing current to the called line and applies ringing tone to the calling line. And there's also DC voltage that's across the line. When you as the called party pick up, you're closing the DC path. The ringing current is 90 volts at 20 hertz. Okay. So when you pick up your phone, you're closing the DC path. A relay operates in the connector, disconnects the ringing current, and cuts through the talking path between the called party and the calling party and the called party. And then that connector waits for both parties to hang up and then disconnects the whole switch train. Party lines are a little tricky. As I said, you can get two party lines very easily depending upon which of the two wires you send ringing current down. You can get four-party selective ringing by also superimposing 130 volts DC on top of the 90 volt ringing current and putting a rectifier in the or Zener, something anyway, something extra in the phone.
We had that too. We had that later on. Yes.
Okay. Yeah. And then the last thing was just different ringing patterns for ringing different parties.
Mm-hmm.
Many of us have once in a while accidentally touched a hot 110 volt AC wire and said, ouch, gotten that jolt. If you want something exciting is to actually be touching a terminal when it's got 90 volt, 20 hertz ringing current on it. Because you can actually feel the 20 hertz, it feels different from 90 hertz. I've done that working for Dorm Phone. Anybody else?
Well, you're alive to talk about it, so that's good.
Yes, it wasn't wet.
So if you still have a copper wire pair in your house, can you use old equipment? Is it still compatible with the old ringers, the mechanical ringers and the mechanical dialing, or is that completely incompatible at this point?
Well, the interesting thing is, I think, as time went on, more and more people got touch tone phones, and fewer and fewer people had dial phones. By the time, the early electronic switching systems, number 1 ESS, actually still used metallic crosspoint switching. They were reed switches, they weren't crossbar switches, but they were still metallic crosspoints in the number 1 ESSs of the 1960s and 70s. So they actually also had line relay circuits that used actual relays. And the interesting thing was that if you dialed a number in a number 1 ESS, the CPU was actually counting your dial pulses. And it was doing this, perhaps for hundreds of calls that were dialing simultaneously, but it was counting the dial pulses, whereas touch tone was an electronic circuit that said, okay, here's the number. By the time the electronic switching went to all electronics and there was no more metallic crosspoints, they really wanted to get away from dial, because that was, required extra hardware, required extra stuff. In very few jurisdictions in the US were the Public Utilities Commissions willing to allow the phone companies to cease recognizing dial pulses. New England Telephone, I think Massachusetts was particularly sticky with New England Telephone. Every switching system in Massachusetts had to, that was regulated, had to listen to dial pulses, be able to register dial pulses. So I think it's just the, if you have voice over IP service today with a regular telephone plugged in, or you get your phone service from your cable provider or Verizon Fios, it looks like a regular phone wire in your house. And there's a little unit that's still generating ringing current. It's probably 20 volts at 90 hertz, because it doesn't need to go down a mile-long phone wire. But it's still ringing current, and it's still got, talk battery. Again, not 48 volts, because it doesn't need to get that far. But it's still got talk battery and still recognizes off hook in the same way. Yeah.
Yeah, but if you have one of these VoIP systems like Comcast, you will not be able to use a dial or a pulse phone.
Right. Yep, got rid of that finally. And that voice over IP service is not is an unregulated service.
Right.
It's not regulated by the state.
Right.
I said the VoIP actually acts as data. It's just part of your data demand on the internet service.
Right. Once you get to the other side.
Sure. I still have a POTS line. Do you think that those would be offered for much longer?
What Verizon is trying to do, what all the phone companies are trying to do, is they're trying to get rid of their copper wire plant, going back between your house and the central office. What Verizon would like to do, if they're basically, if your phone line stopped working because there's a break in the cable or water got into a splice case and corroded it and the copper wire would no longer work, what they would do, and the state regulators will now allow them to do, is they will move your telephone service to optical fiber, not necessarily by moving you to their Fios branded service, but basically they would be providing you regulated telephone service over optical fiber. So you would no longer have copper wires going back to the phone exchange. The copper wires would only go to the box on the side of your house, where it would then connect to a fiber optic going back to the phone exchange. And Massachusetts has allowed Verizon to make that substitution as long as they agree to keep that telephone service as in the regulated telephone service category.
The advantage of a POTS is when you lose power, it's the one thing that still works.
Well, that's right. And so if they switch you over to this regulated telephone service over fiber optics, then you're reliant on the battery backup system.
Yeah.
Yep.
Thanks.
It's just a little bit after 12. Some of us have other commitments. We have to hit at 12. Ken has a life, I'm sure, outside of the Zoom. Really appreciate your talk, Ken. Very interesting, very reminiscent, especially all the noise and how quiet it is nowadays to make a call.
Thank you.
Thanks, folks.
Thank you. Very interesting.